So today the topic is about machine learning enables seismic performance prediction of movement resisting steel frames. That's a very solid and relevant topic, especially especially with the growing interest in combining structural structural engineering with machine learning. Machine learning seismic performance prediction of movement resisting steel frames with semi-rigid conditions with semi-rigid conditions. Like introduction, earthquakes pose a significant threat to safety and performance of civil engineering structures, particularly steel buildings located in seismic-prone regions. Among various structural systems, movement-resistant steel frames are widely used due to their ductility, energy dissipation capacity, and ability to withstand lateral loads. The seismic performance of these frames largely depends on the behavior of beam to column connections, which in practice exhibit neither perfect ridge or not perfectly pinned characteristics, but rather simulated behavior. The traditional methods for evaluating system performance, such as nonlinear static like pushover, such and analysis and nonlinear time history analysis, are computationally intensive and time consuming. These methods require detailed modeling, expert knowledge, and significant computational resource, especially when multiple structures, configurations, and ground motion records are considered. As a result, they are not always practical for rapid assessment or real-time decision. Data and features. The performance of machine learning models largely depends on quality and representatives of the datasets used for training and testing. In this study, the dataset is generated through detailed nonlinear numerical simulations of movement resisting steel frames with semi-rigid conditions subjected to various seismic excisions. Data generation, like a series of steel frame models with varying configurations and developed and analyzed using structural analysis software such as OpenSeas. The models incorporate material and geometry nonlinearities along with realistic semi-rigid condition behavior defined through movement, rotation, relationship. To ensure diversity and robustness in the dataset, the following variations are considered, like number of stories, example low, mid, and high-rise frames, span length and bay configurations, beam and column section properties, connection stiffness levels, different earthquake ground motion records. Sensor and design inputs. In the proposed machine learning framework, input data is derived from two primary sources: design parameters, sensor based measurements, real-time prediction or future implementations, structural health monitoring system. The integration of these inputs enhances both predictive accuracy and practical applicability. Design inputs for machine learning based for model based parameters. Design inputs represent the inherent properties of the structure defined during modeling and analysis. These parameters remain constant for a given structural configuration and play a critical role in determining seismic response. Number one, geometric properties like number of stories, number of bays, span length and story height, and frame configuration. 2. Section properties. beam cross-sectional area and moment of inertia, column cross-sectional properties, and sectional type. Third one, material properties, yield strength of steel, modulus of elasticity, strain hardened characteristics. Fourth one, connection properties like initial rotation, stiffness, moment rotation, relationship parameters, connection strength, stiffness ratio. And sensor inputs are obtained from instrumentation installed on structures. These are especially useful for real-time prediction, model updating, and, and structural health monitoring, like acceleration measurements, displacement measurements, strain measurement, velocity sensors, environmental and ground motion sensors. The combination of design and sensor enables the two key applications like data-driven prediction. Design inputs used to train machine learning models. Sensor inputs used as a real-time features for prediction. Second one, model updating. Sensor data helps to refine and recalibrate machine learning model, reduces prediction error over time. Dataset curation. Dataset curation is a critical step in developing reliable machine learning models for seismic performance prediction. It involves the systematic generation, organization, cleaning, and validation of the data obtained from numerical simulations that were available, and sensor measurements. The goal is to create a high quality, diverse and representative dataset that captures the complex nonlinear behavior of movement resisting steel frames with simulated connections, data collection and assembly. Modeling, modeling and evaluation. This section describes the development of machine learning models for predicting the seismic performance of movement resisting steel frames with semi-rigid connections, along with the evaluation procedure used to assess their generalization capability. In machine learning model development, the relationship between structural parameters and seismic responses is highly nonlinear and complex. To capture this behavior, several supervised machine learning algorithms are implemented and compared, like selective models, like artificial neural network, random forest, the support vector machine, gradient boosting, model architecture and configuration, Art, artificial neural network (ANN) input, training procedure is uh, the curated dataset is to split into training and training sets. The models are trained using training data. Hyperparameters are optimized using grid search, k-fold cross validation to improve robustness. Early stopping is used for ANN. Regularization techniques are applied. Evaluation metrics like model performance is assessed during standard regression metrics, mean absolute error, root mean square error, coefficient of determination. Like validation with simulation results, the trained machine learning models are validated against results obtained from nonlinear time history analysis conducted in OpenSys. Selected unseen cases are used for testing. The machine learning predictions are compared with simulation output. Acceptable error margins confirm a model reliability. Validation and testing. Validation and testing are essential to ensure that the Developed machine learning models to provide accurate, reliable, and generalizable predictions of seismic performance for movement-resistant steel frames with semi-rigid conditions. Connection. The data splitting strategy, like the curated dataset is divided into three subsets to ensure unbiased model evaluation: the training set, validation set, testing set, and cross validation is to enhance the model robustness and reduce overfitting. K-fold cross validation is employed. The dataset is divided into k subjects, typically k is equals to 5 or 10. The model is trained and validated k times, each time using a different subset for validation. The final performance is obtained by averaging the results. This approach ensures that the model performs consistently across different data partitions. Comparison with numerical analysis. To validate the reliability of machine learning predictions, results are compared with outputs from detailed nonlinear time series analysis conducted using OpenSys. Predicted versus simulated values are plotted. Deviations are analyzed for critical response parameters. Acceptable agreement confirms model validity. Error distribution analysis, like residual errors. Distribution plots are used to check for bias and variance. A well-performing model shows symmetric error distribution, minimal extreme deviations. Conclusions. This study presented a machine learning based framework for predicting the seismic performance of a movement resisting steel frames with semi-rigid connections. By integrating structural design parameters, connection characteristics, and seismic input features, the proposed approach effectively captures the complex nonlinear behavior of such systems. A comprehensive dataset was generated through nonlinear time series analysis using OpenSys, incorporating a wide range of structural configurations and ground motion records. Various machine learning models, including artificial neural network, random forest, and support vector machine, were developed and evaluated for their predictive capabilities. The study also the study also highlights the critical influence of simulated connection behavior on seismic response, emphasizing the importance of incorporating realistic connection modeling in both simulation and data-driven approaches. Furthermore, the integration of sensor-based inputs offers the potential for real-time prediction and structural health monitoring applications. Thank you.